Hey, welcome to NPLAN's Paper Club. Today I'm going to present the paper called Cooperative Graph Neural Networks. They call it cooperative because they present they kind of give each node in the graph the ability to choose actions, almost like in a game, but it's not a zero-sum game, it's a cooperative game. So there is no equilibrium or anything. It's maybe more similar to reinforcement learning. But we'll see. We'll have a discussion later. So basically, the main idea is that uh, GNNs struggle with a few problems. We covered those here a few times. Namely, the WL test puts a upper bound on the expressive power of GNNs or on message passing GNNs, which means they struggle to distinguish between isomorphic graphs. I will see a few examples later. Uh, but there are a few other problems, kind of related. And the main one that they cover here is that if you want your nodes to learn from neighbors many hops away, you have to have a very deep channel, which comes with lots of problems, over squashing and over smoothing. Again, we'll look into this during the paper. And this paper proposes a solution which basically allows each node to choose when to propagate information or when to take information and when to not do anything, right? And uh, it's and it's learned. Basically, you allow the nodes to learn what's the best action for the node in this specific graph, right? And they claim this solves a few of the problems. Uh, the theory is kind of weak because it's not specific to this setup. They can borrow ideas from other papers, other setups, and make claims, which fair enough. But again, we'll see the details. Experiments are not groundbreaking. I think that's why the ICLR reviewers were not happy also. But that's not the point. The point is they use very basic GNNs like GAT, GCN, like the from 2017-18, and to beat too much baselines from the most modern, most advanced GNNs, right? So they are saying that next step from this would be using more advanced GNNs because you can basically plug in any GNN into this architecture. Maybe that will be the next revision, right, for ICML maybe, but we'll see. Anyway, so that's the high-level abstract. And any comments before I go into the details? All right. So here on the right, we have this example where we have a small graph, and they want to show. Well, they first they speak about um, over squashing. Let's talk about over squashing because it's a common problem across GNNs. Basically, the idea is I think we covered another paper a while back solving this issue. The idea is that if you want to propagate messages from nodes that are many hops away from the current node, uh, uh, we have to squash information into into node embeddings, or even maybe an edge embedding, right? Whatever you are doing, you have a lot of information, and it has to be squashed into single nodes to be propagated to, let's say, node V. And if you want everything from far away to come to V, you need to squash information. That may lose information, uh, and that's one limitation. Normally, these problems are solved by adding an extra uh, graph on top of your current graph. So you would allow extra edges to go far distances, right? Or you would do subgraph extraction kind of methods. Here they are proposing a different solution, which is you allow each node to choose what information to take and what information to pass. Okay, and I don't exactly see how that solves over squashing because if anything, you are limiting how much information can pass, right? Uh, but maybe that solves the problem because you don't pass information that doesn't matter. You only pass information that affects the node, right?
I think all of their proofs rely on the idea that at most the graph can have the same connectivity as the original graph.
Mm,
So with less connectivity, you have less over squashing and less like less
mm.
bottlenecks. That's my
Right,
understanding.
exactly. So you basically allow the node to not take irrelevant information. It's like an efficient way to pass the information, right? But they don't really prove that, right? As you said, Peter, proof relies on the fact that you don't pass too much information, but there is no evidence, no proof showing that you pass the information that matters. There is no. So if you see the proofs, but basically they say a neural network exists that can solve this problem. But how do you find that? That's the open question here. The proofs are more like about existence of solutions, which is not uncommon actually. These sort of proofs are quite common because you can't really prove that. It's hard to prove that uh, after training with Adam or whatever optimizer you are using, you will find the network that solves your problem. Right? That's much harder. Anyway, here in the diagram, in the figure one, they are showing this case when uh, node W listens only to node V, which means information coming from the left is not propagated into W, right? You can also use this sort of structure uh, also to allow to kind of force directedness in your graph. We'll speak about this later also, but as you can see, you only allow from information from the left, right? But you don't enforce that. You let the nodes choose to act like this. That's the flexibility. Okay. Any questions? We spoke about over squashing and limiting and allowing the nodes to choose what information to take. Okay? Um, and the motivation is that again they motivated saying more flexible information. They allow more flexible flow of information. We discussed this part and um, right. Let's look at this other example. Um, um, this is an example. It's quite complicated actually. I found it quite hard to follow exactly what's happening, right? Basically, because
Same.
for each layer, they allow each node to choose where to take information from and where to propagate it, which also includes, which means four choices, right? You can isolate the node, which means nothing coming in, nothing going out. You can only take information, you can only pass information, or you can do both. So doing both is what standard message passing does. So they call it standard, right? The others are limit the information flow. I would try to go through each of these cases, but I find it quite confusing because you have like three layers here, right? And then first layer, you node V only takes information from the left. Like level one, it only takes information from one hop, right? And so on. So I think here you have colors mean. So it means something. So I think pink means take, blue means pass information. Uh, because you can pass information, but the other node may choose to not take it. Right. So message passing is done only if both nodes choose to pass and receive information. That's what this example shows. And you can limit that space. So each node can choose a different strategy for each layer. That's why it gets kind of complicated. It's a lot of flexibility. And obviously these choices are learned. And we'll see in a moment how the learning is done. Comments? No? Okay, I mentioned that the four things like standard is broadcast and listen. Then you have only listen, you have only broadcast and isolate. Okay. They speak about the contributions. Um, they propose a novel flexible message passing mechanism, which fair, right? I haven't seen anything like this before. This is very flexible, also good, which allows to effectively explore graph topology while learning. Um, I guess that's the point of the whole paper. Um, They give a discussion about expressiveness with WL1, the one-dimensional Weiss-Filler-Lemon algorithm. If you are not familiar with this basically this WL algorithm is a coloring algorithm which iteratively colors nodes, and with the objective to uh, you use the final coloring to distinguish between graphs. Okay? And there are theorems showing that message passing cannot distinguish graphs better than the 1WL algorithm. Okay? So it's like an upper bound of message passing GNN's expressive power. Expressive power means can you distinguish between isomorphic graphs, right? Because they are kind of similar but not exactly the same. And they're showing that they give examples. I think not even proofs, examples that uh, on some graphs the WL1 test uh, fails, but this new algorithm can distinguish between isomorphic graphs. And again, it's a little bit questionable because it relies on adding randomness, because they rely on sampling, which means the proofs are actually very similar to other previous methods, which would solve this WL uh, limitation by adding noise to node features. This is actually quite similar to that, except it's not noise, but the randomness actually helps solve the problem. And then they do experiments showing that this new GNN, which they call co-GNN, cooperative GNN, uh, performs just as good as state of the art and much better than the classic GCN graph-stage GAT methods. Those are from 2017, the original GNNs. Okay? Questions about contributions or comments? All right. Let's look at a bit of background. GNNs. So this formula up here is a general form of how GNNs operate. So you have two functions. You have the update. 3L is the update function, which is usually nonlinearity. And you have the aggregation function, which is like a sum or average or max, some sort of aggregation. So aggregation means there are messages coming, but let's not call it messages. So you have a node, you have neighbors, and then you aggregate features from neighbors, like sum them, average them, whatever, and then put it together with the current nodes embedding, which is this HVL. That's the current node embedding, right? And then the two of them together are updated with a nonlinearity. And then this new thing becomes the current node's new embedding. And then you do this many times um, until you find the final embedding for each node. Okay? Questions here? Okay. Um, so the formula below is a more specific version, which is for message passing. So message passing means uh, that's basically what most GNNs or the classic GNNs do. So you have learnable weights, W, S, and W, N. So those are learnable weights. Sigma is the nonlinearity, right? We actually replace those generic functions with specific ones. There is a sum here. Uh, so you sum the two the two embeddings, the current embedding with the weight and uh, the aggregated embedding, and then you pass it through nonlinearity. Okay, that's how message passing works. And then you would have different aggregations here. If it's a GCN, you would have this graph convolution. If it's a GAT, you would have attention on each to weight each neighbor's input, and then you would learn those, right? So those functions, the C would define the specific message passing GNN, would be a GCN. GIN is another version. It's like a graph isomorphic networks, which basically has an epsilon here. So you make it the current node embedding a bit more special, okay? To distinguish it from the neighbors. They because this one was designed to solve the isomorphism problem. This is another commonly used GNN. Okay, cool. Now, one more important thing here. We are going to use softmax as nonlinearity, uh, but we will also, because we will also train to big propagation, and we don't know how to calculate gradient for softmax. A common technique to solve this is replacing softmax with a Gumbel softmax
Wait, we do know
estimator.
how to calculate the gradient for softmax. We don't know how we don't know how to calculate the gradient for
Sample.
sampling from softmax.
Yeah, sorry. Thanks, Peter. Yes, because there's how to calculate gradient after sampling from softmax. That's important. Yes. Thanks. Because as I said earlier, we are going to estimate distributions and then sample from them, which will introduce some randomness, which will also solve the isomorphism problem, right? And then, but we don't know how to calculate gradients from the sampled values. And we will use this Gumbel estimator, which is a common way of replacing this sampling with a differentiable function. Basically, the estimator is given down here. So on the forward path, we just do normal softmax. On the backward path, we use the Gumbel softmax to calculate gradient for sampling. Okay? Other comments here? Okay. A bit of related work. I think the first thing that I thought about here was why not use a graph transformer, right? Because graph transformer operates on the entire graph, which means it can pass information from everywhere in the graph. And it also has this graph positioning embeddings, which depends on your graph kind, right? If you have a directed acyclic graph, you would have a topological sort, or if you have a normal graph, you would have some distance-based positioning, right? So these things exist, but there is a problem with transformers, graph transformers. They are very inefficient. If you check the PyG documentation for graph transformers, I think they recommend to not use it on graphs larger than 100 nodes. It's actually quite computationally expensive. So here, I mentioned the other method which solves the isomorphism problem by adding noise, and we will use similar proofs here. Other methods to help is, I think that's all here. Oh, you can also add extra connectivity. I mentioned this earlier also. You basically, if you want to pass the information from far nodes into the current one, you can add this extra node, extra edges or an extra network on your current graph to allow message passing from far distances, right? Without over squashing. That's another thing. But they mentioned here one work that's most similar to this one, which is in the bottom here. I think they say our work is related to the earlier work of Lai, where the goal is to update each node using potentially different number of layers, which is achieved by learning the optimal aggregation depth. And so here, each node gets to choose how deep to go, because this is useful because some nodes, sometimes you would have a long chain, right? In those cases, you would want your node to have a long, deep layers to achieve longer distances. But other times, when you have a more dense graph, you don't want that because then you would squeeze all the information into here. Okay, so this other work proposed to allow choosing uh, to allow learning how many layers to choose for each node. Uh, of course, here the methodology is different, but also we allow not just the depth, right? We allow choosing how to pass information. Okay, but that's the most relevant work. Okay. Should we talk about the architecture? It's actually not too complicated. They basically learn two GNNs. There are two GNNs here learned together. They don't give lots of details uh, because I have to guess that these two are trained together, but I didn't see it mentioned explicitly. So basically, you have two networks. One is pi, the other one is eta, and they can be here, and they can be anything, right? Uh, because so they experiment with using more simple GNNs like GCN, GAT kind of methods. And each of them can also choose to use different aggregation and update functions. And we will see in the experiments that that actually matters. Uh, so the first one, the pi network, uh, learns to choose the action, right, and then sample from that action. So pi learns the best action, one of the four actions we discussed before, the standard one, broadcast, listen, or isolate. That's what the PyGNN learns. And then we have this other one with an eta, which learns how to update, right? Because each node uh, has a action, but then you also want the GNN that actually does the updating. Right, and then here it says if the action is isolate or broadcast only, so there is nothing coming in, right? Then the neighborhood set is empty. On the other hand, if it's listen or standard, so there is information coming in, then you would actually propagate information from the neighbors. Okay, so you give a lot of flexibility. First, you let each node to decide do they want to broadcast information, and then you let each node again decide if they want to take the information coming in. Okay, and then those are done with two different networks. And importantly, the actions are learned probabilistically. So you have a softmax which gives you the probabilities, and then you sample from those. Okay. Questions here? Okay. Um, go down, and then they also talk about this. This is important. They discuss four different GNNs. So there's the sum GNN, which basically sums the neighborhood. There is the mean GNN. You can guess from the signs, right? The sum, mean, which averages the neighborhood, the convolution with a star, and epsilon is the gene. This is basically like a GCN, but the current node is taken with an extra epsilon weight. If you search for the GIN update formula, you'll see the difference. There is like a 1 plus epsilon times the current embedding, and then plus the sum of the remaining embeddings from the neighborhood. Okay, so we discussed those four um, methods. To be fair, they call these basic GNNs, but GIN is, I think, is still close to state of the art. This is actually a very powerful method. Okay. And then we will choose from four of those as our ETA network or Pi network. Okay? So we get to choose which one goes well. Which also I see this part a bit of a limitation because I would rather have the model to choose what network to use because I don't want to experiment with 100 different GNNs in two places. So we even have combinations to figure out which one works best well, right? It becomes a bit limiting. So if there was a way to also keep this more flexible, maybe use one of the more modern GNNs in both, and then not worry about choosing anything, right? That would be more useful, I think. Anyway, let's scroll down. Okay, another complicated example. Let's zoom in a bit more here. Okay. So this example here, this basically shows with different actions. So listen, LL is listen, S is standard, right? So for each node, for each layer. So this index is on a H. These represent the layers, right? And then for each layer and for each node, we have a different set of actions. You have three. You have sets of three because you have actions for each next layer, okay? And for each node. I guess we could go into each case and see how information is passed, but the left one is the original graph, this. And then based on the actions for each node, so you would have, for example, they say node U, right here, if you look, node U has listen for the first layer, and node V has also listen, and W have listen, and then all others have standard for layer one, right? So based on that, you basically add directions, right? Uh, if the node only listens, there is an incoming edge, but not outgoing. So you turn this into a directed graph, and you did do this for each layer. Okay? And this actually breaks down the information flow. After the third layer, you see there is no more information flow between V and W, which solves the over squashing problem, which is why they give this example. Okay? Questions here? Okay. Go down. Model properties. Now they discuss a few properties about the model. Uh, so this is task specific, right? Because they say normally GNNs are generic for all tasks, right? Here we uh, we allow each node to listen to the information only from relevant neighbors. So relevant is in quotes because the node decides what's relevant, what's not relevant. Okay, so each node becomes no, the learning for each node becomes more task specific. We spoke about the directedness, right? If you look at the example up here, uh, we turn the graph into a directed graph because the information flow becomes directed now. Normally, that's not the case, right? They call it computational graph, but I guess we can call this computational graph, right? If you look here, you see how information is passed. You can call it a computational graph in a way. Okay, it's dynamic. Dynamic means that for each layer, the computational graph is different, right? Oh, there is a better example of the computational graph, which basically means how the information, it becomes a tree, right? How the information goes from each node into the current node, okay? And it changes for each layer. And then there is also the most efficient one with the red colors. I found this a little bit confusing, but I think the idea is that um, nodes get to learn how to pass information. Same old idea, and this changes dynamically, as in for each layer we have a different path for information flow. Okay. Um, get the same. All right. So they also say that this comes back to the isomorphism test because similar to that, the standard message passing is completely determined by structure of the graph. But here, it also is determined by the features, which is interesting because as you update the features, nodes also get to choose how to, and you update it dynamically also. Nodes get to choose how to pass information. So the graph changes for each layer based on the features of nodes, okay? Which is quite interesting. And I think that's also novel, right? Because message passing is not only based on graph structures, but also based on node embeddings. So this may also be true for transformers, actually, right? Because if you have a graph transformer, you now passing information everywhere, and based on node position embeddings and the features, the transformer learns different attentions. So the graph structure is not as important, except for the position embeddings. But here they say that compared to normal graph message passing methods. Here we also take into account node features to decide how information flows. Okay. Take a break. I'll take a breath for you to maybe think of any comments, criticize the paper.
One thing I was wondering, I mean, over squashing and bottlenecks, I don't think you can be addressed by what I'm about to suggest. But I was like, I wonder if you can add additional features. Like, I think they even suggest something like adding random features to nodes.
There are papers that do that actually.
In order to deal with a lot of the issues that they discuss.
Yeah, there is work that does that. If you look at the relevant work, related work, some papers did that, like adding random features.
Because I feel like that's a much simpler method than this.
Yes.
And once we get to the results, I guess we'll talk about how good this method is.
Yeah, exactly. Yeah, there is work doing that actually. Okay. They also talk about asynchronous updates. I haven't read this other paper from Faber and Rottenhofer, but someone is ringing my door, but it's okay.
I
This
didn't
other
get what
work,
that meant. Like, how are these updates asynchronous?
because so first you decide, uh, uh, wait, you first decide how to pass information, and then you update, then you receive information. That's my guess, right? Because you don't update each node at the same time. I think that's what they mean. But maybe I don't really understand that either, to be honest. Um, there is work showing that it's not
Actually,
all.
that does kind of make sense, but not, because I guess what they're saying is like you could skip a layer for one node, and so you're not updating at every layer. So you're not updating all the nodes at the same time. You're updating the nodes at different times.
Yeah, exactly.
I guess that's it.
Based on the information flow, you update nodes at different times, right? Yeah. Um, so there is another important thing here. This was the main concern I had before reaching here. That is this too expensive? Are we training two models, right? Do we have too many parameters? So they claim that the running time was efficient, but I didn't see any numbers how efficient. And then they also say it's also parameter efficient because they use the same policy network, and as a result, a comparable number of parameters to their baseline models. I would like to see some more details here because I thought we have two different channels, right? So that part is also, I guess I'll trust that it's efficient, but I would like to see some more details. Cool. They also talk about expressive power. So they mentioned that the purpose of this paper is not to improve the expressive power, but they talk about it anyway. And then they have this proposition that says, basically here, if you read the, let me highlight that here, right? If you have two graphs, right, with vectors, edges, vertices, edges, and the features, x's are the features. If there are two non-isomorphic graphs, then for any threshold delta, you choose a threshold. There exists a parameterization of cooperative GNN, so you can train a cooperative GNN, right? Using sufficiently many layers. Again, maybe too many layers. We don't know how. I wish there was some more explanation of how does number of layers, for example, relate to how delta has to change. That satisfies that the probability of the trained model, no, the probability of the node embeddings, which are the z's, right? Z's are the node embeddings after L layers, are different, is larger than 1 minus delta. Okay. So basically, the probability is not zero. So the question is, like what's the relationship between delta and L, right? And then they also have a funny thing here. Um, uh, I guess no, that's fine. So they said that's just that improves the expressive power as compared to 1WL test, because the 1WL expressiveness doesn't have this property here, right? And then they give an example how that's possible, which makes sense, right? Because you break the information flow, you end randomness, so it makes sense that you would improve the expressiveness. Okay. Um, Here they say our result is analogous to GNNs with random node features, right? They basically rely on the sampling process to add randomness in the features instead of adding actual randomness, and then that's how the result comes. Okay. Uh, there are also other works, the subgraph extraction methods. I think this paper is quite popular, actually. There is a paper using subgraphs to break the isomorphism problem. But anyway, any comments here? They do mention that the co-GNNs are not designed for expressive power. Fair enough. It's just a nice thing that comes on the side. Yeah. The other property, dynamic message passing for long ranges, for long range tasks. This is an important problem because if you have a well, we like to talk about Gantt charts at Emplan. Right? If you have a Gantt chart, dynamic acyclic graph, those tend to be like long, but and very sparse. So your nodes don't have lots of connections, but to go from the early node to the late node to pass messages between early and late nodes, you need hundreds of layers, right? And that's not going to work, because if you do that, the neighborhood will be squashed, and then you won't be able to pass the information anyway. So that's a problem, right? So normally these sort of problems are solved by adding extra edges between the far distance but relevant nodes. You can do it randomly. You can kind of manually choose how to add those, but there is work studying this approach. So here, what they show with this theorem is that if you have a connected graph, right? Connectedness makes sense. If it's not connected, you can't pass messages anyway. Then there is a k, and so that for any target node and any k source nodes, so you have a target node and source nodes, and then if you choose a differentiable compact f, let's say good function f, the Gamble softmax does satisfy this condition. There exists an L layer cooperative GNN. Again, exists GNN. Right, so we should be able to train such a model. Computing the final node representations so that the probability of the final node representation being too close, right? Too close to what close enough, let's say close enough to what the function returns uh, is large enough. So you basically you can converge to the to you can find a function that can converge to the final node representation. Okay. Again, we don't know how efficient this process is, how delta relates to L, how many nodes you can connect to each other, and so on. But it shows that such a model can be trained. Okay? In theory. Questions here? Cool. They explain the methods here, and then they say that this follows from two findings. Okay? First of all, features of K nodes can be transmitted to the source node without loss of information. But it's connected, and then it's and we assume that the nodes will not learn stupid things, and they will allow to pass information. Right? That's an assumption here. And the second is that the final layer is an MLP, which can approximate any differentiable function. Right? There's the universal approximation theorem. And it's kind of funny that they rely on this because in your GNN, you always have an MLP at the end, and then you assume that your MLP will be able to approximate anything, right? So the GNN message passing part becomes kind of irrelevant for the proof. So I guess you could just have an MLP, right? That would be no, you wouldn't be able because GNN allows you to pass information. So you need both of them. You need the message passing to pass information, but also you need the MLP to approximate the function uh, uh, properly. As you can see, the MLP approximation is a fairly old result, and it's a very commonly used result also. Okay, comments here? No? Okay, they speak about over squashing. Um, I mentioned this that the common technique is to rewire the adjacency matrix to increase the information passing, but there is also a well-known upper bound using the Jacobian of over the embeddings, which puts a upper bound of how much information can pass. Uh, but we don't need to go into details here. I don't think this is very relevant to this work. Right? It's like more general result here that over squashing means there is a limit how much information can be passed. And over smoothing is related but different. So over smoothing means uh, if you have too many layers, you will average out everything, and then all nodes will end up with the same embedding. Okay, there's the other problem. And and then they say that over smoothing can be mitigated with gradient gating. So you basically will have a gating mechanism to not which decides whether to add information or not, which is kind of similar to what we do here, right? But what we have here is a bit more flexible. Okay, and then they say because gating works, it should also work because this is more flexible. Okay, experiments. So the first experiment is synthetic on synthetic data. So they build this kind of a funny problem actually. I found this a little bit new. I haven't seen such problems for GNNs before. Basically, they design a tree, and then they give this task here, which is given a rooted tree. So this is a rooted tree on the right. Predict the average of the features of root neighbors of degree 6. So there are two things here. First, you need to find the nodes which have a which have distance 6. Right. So basically, you have to go up and then down, right, to find the distance 6, and then you need to be able to average them. So those are very different tasks, which is why a simple a single GNN struggles with this because it can either find the distance 6 or it can average, but usually they can't do both. Which is why this architecture actually works because you can have two models, right? One of them is good at finding the distance, the other one is good at averaging, and then you make the one that's good at finding the GNN that decides the actions, and then you use the other one that decides how to aggregate messages. Okay, it's basically what happens. You can scroll down actually.
Sorry, you just reminded me of
Yeah.
another question I had about this method, because it says it's using two GNNs, but it seems like at each layer you have to query both GNNs like that for that layer. So to me, it's a single architecture actually because of that. Like it's not like if you could call them in series or you could call them independently and then aggregate them in some way. That makes sense. But here it seems like you call layer one of the first one, you sample an action, you call layer of the second one, the first
I
one,
think
and
that's how
you.
it works. Yeah, that's why they call it asynchronous. That's my understanding, but I'm not entirely sure. I didn't see enough
Okay.
details about that, right? But I think that's how it works. No, that would be my
I
guess.
agree. That's what I think. That's how I think it
Yeah,
works too.
mm. There was a message. Side note: my son Rafael is at Oxford studying computer science. I don't know whether he knows any of the paper authors. Oh well, Bronstein is a famous professor. He's at Oxford. Oxford has a also has a history of writing good papers for graph learning. I assume the first author is a PhD student, probably, and there is another professor also there.
Oh, great.
Okay, cool. So the setup for the experiments, they use the GCN uh, and the GraphSage. GraphSage is another version from GCN, which is basically GCN but subsampling. So GraphSage is a way to make GCNs work with large graphs. So you can subsample from sample subgraphs from the graph efficiently. GAP is graph attention, so you have weights, learnable weights on each of the neighbors. Some GNN, mean GNN are basic methods. You basically just sum or average neighbors. Those are from, I think, Hamilton's book. I think Hamilton has a book for graph learning, graph representation learning. So here, they basically run the experiment and then see which one of those four methods. There is no gene, by the way. There is no graph isomorphism network here. They run the experiments, see which one of those four works best for each of the two tasks in this dual task problem. And then they plug in that GNN for the relevant part of cooperative GNNs. And then they beat each individual one. I guess that makes sense, right? Let me here. So they report mean absolute error, and so low is better. And then you can see that this is the result for the overall task, right? You have to solve both problems here, and none of the standard methods is able to solve both problems. But they actually mention here that, for example, mean GNN is very good at averaging. Obviously, right? If you tell it what to average, it will be if it average very well, but it can't find distances. So I think they say Sage is very good at Graph Sage is very good at finding the distances. Um, uh, but then Sum is also good at finding distances. So they end up using sum and average as a result, right? Okay. If you use mean, it can't find distances, so the result is bad. Funnily enough, they found a problem where the basic GNS perform almost as badly as a random guess. Right? That's interesting. Okay. Let's go down to more real setups. So node classification. Now, this is interesting because we have these heterophilous graphs, which is very important because originally GNNs came with this assumption that neighboring nodes are more likely to have the same label. And those are called homogeneous graphs. But then people discover that if you don't have this property, those are called heterophilous graphs. GNNs don't work so well, right? There is worked with I think this one is a. I shouldn't have clicked on that. There is a review paper studying different GNNs performances on heterophilous graphs. And in real life, you see these sort of graphs quite a lot, but not always. Right? If you have a social network, you would assume that you have a lot of commonalities with your connections, right? Or if you are studying molecules, similar, like the neighboring molecules are probably similar. So have some similarities, right? So it's not always a problem, but there are cases when it's a problem. Like knowledge graphs could be an example, right? Depending on what you are classifying. Okay. So here we study real life examples. Let me scroll down. Again, we don't have GIN here. I don't understand why they removed GIN from experiments because that's a very good method. And then we have the those are all large graphs, right? Those are like Amazon ratings. I don't know all of them, but these are all large graphs, so but partially labeled. So you train a model on this, and then you predict labels for the unlabeled parts, okay? But for the unlabeled nodes. Again, I can show that cooperative GNNs are better on most tasks than each individual GNN, right? Some of them don't have much improvement, but some others, like this one, like this Minesweeper, has a good improvement. I guess it depends on the task, but this is good. I would say if you want a better comparison table, you have to add a couple of other modern GNNs. Again, those are from 2017. Okay. Oh, GT is not actually. GT is new, I think. Graph transformer, right? So this one is new. I guess that one is good to have here, but the others are old methods. They also have graph classification. So here, you basically train your GNN, but you don't classify each node, but instead you have a pooling method at the end, which could be like max pooling, element-wise max or average or whatever, to get an embedding for the whole graph and then classify the whole graph. Okay. So those are graph classification methods. And here they don't do as well on all tasks. Because I guess they also have some modern methods here. It's hard to compete with the modern ones. But they again, the cooperative GNNs are better than all the other classic ones. Okay, Genius here. I guess that's interesting. Okay, I think that's all from results. I think that's all. Yeah, conclusions, nothing new. Any comments? We have a few more minutes left.
Not easy to follow.
I tried to explain everything, but any specific questions, Nicola? I can.
It's just a comment because many of this I know just some basics, and to get into it's not easy.
If you want to get into graph learning more, because we covered those here a few times, I didn't want to start from the very beginning, but Hamilton has a great book called Graph Representation Learning. It's a bit old, but it's really good. There's another one. I think the author is called Lean. It's called Graph Neural Networks. That one is more modern. It covers more modern methods.
Okay, can you write them into the chat?
Sure, I think yeah. Hamilton's book is so available free online also. I think the other one is also free.
One thing that I'm wondering is, I know that for graphs, that transformers like GATs are inefficient, but
the GAT is not a transformer. GAT is very efficient.
Sorry, graph transformer networks, GTNs or whatever, like what they mentioned before about using transformers essentially, because I've seen that. But I think that's only the case if your graphs are like really massive, right? Because we're getting to the, if we can process 10,000 or 32,000 sequence length sequences for like by LLMs, that means that we can use transformers for graphs that are of the same size, because actually with graphs, the transformers would be connecting, would perform like even more sparse attention.
There is a nuance here, right? So when you train a language model, you have a lot more data. So if you have a massive model but very little data, you may not be able to train that.
That's fair. That's fair.
But also, when you train these massive models, it takes a month and a couple of data centers. Right? So it's actually funny. I remember data centers. At New Ribs, there was a panel discussion. There were people from Meta and Google. Someone asked them, do you think a student can train an LLM? How can a student train an LLM The answer was like, I don't know. Usually we use multiple data centers connected with efficient cables to do that. It's almost ironic. But anyway, I got sidetracked from the question.
Mm-hmm. No, but it's a good point. I don't know how a student would train an LLM, but we can fine tune LLMs, right? So you could, in theory, you could quantize, do everything to make the LLM as small as the transformer as small as possible, and then train it.
Yeah, I think here they use the 100, so nothing too big.
I really wonder, and this is definitely a personal opinion, like what is the future of these message passing networks? Because I don't really, like if you look on these benchmark tasks, not the ones they have here, but the ones like in Open Graph Benchmark, basically transformer-based architectures are at the top. So I wonder, I think something is going to have to happen to make these models a lot more effective, like to basically show that graph structure is important. Because you can come up with like the synthetic example that we saw where it's obviously important. But then in real world data sets, how important is it?
Oh, it is important because graph transformers still do okay, right? Because the position embedding is important. And if you have a tag or any graph, really, you can add the position encodings to help with that. But I agree. Message. I mean, in general, if you add inductive bias, you should be able to help the model. And it's hard to say. And there are a few comments here. Yeah, Julian, but those the Mistral and Mixtral are for language models, so it's a bit. So Mistral does so well. It's not too different from normal transformers, but it's trained on very well curated data. Mistral is a mixture of experts.
Yes.
Of 8 models, again done very carefully. Right? So a lot of hand tuning and data curation went into it.
Yeah. Still, I thought it's an interesting thing to think about. I mean,
yeah. Also, now people are working on new architectures that will replace transformers. So we'll see what happens next.
Yeah. Which ones are you most interested in?
Like Hyena, Mamba, those new language model architectures, which are not transformers, they seem to be on pace to replace transformers.
Yes, these are the state space network.
Yeah.
The Mamba chat, you mean?
Yeah, well, yes. Yeah. Maybe we should cover those papers next year, actually. I think it's time we cover those. Mamba is only 2 weeks old, I think, maybe 3 weeks. We should go over that.
I had a quick look at it. It is very interesting.
Yeah, it was a big theme at NeurIPS also. So we don't have a paper club next week, Christmas break, but next year we'll look into one of those new architectures.
Great.
Cool. Thanks all. We are over time. Take care.
Thank you.
Thank you.